NO2, this stuff here, which is the, sorry, I can't see it there, so the NO2 that we can see there, okay? That's the brown colour we can see in the syringe. This is not the only gas in there though. Of course there'll be some air as well, but that's not reacting with it. The NO2 particles react with each other to make another gas called N2O4. Because there's only 1 mole of this for every 2 moles of this, that means that, so 1 mole of this for every 2 moles of this, that's what I do it. It means that this one takes up less space. There are some gas laws that we don't worry about at this level of chemistry or physics, but basically a mole of a gas at any given temperature takes up half as much as 2 moles of gas. It takes up half as much as 4 moles of gas. Okay? So the space, if they are in the same concentration, then the space taken up by the N2O4 would be less because there's only 1 mole of it. Okay? That's important for what we're about to look at. We're going to be looking at 2 key ideas. One is pressure and the effect that pressure can have on an equilibrium system. The other one is temperature. One of these reactions, forward or reverse, will be exothermic, and the other one therefore will be endothermic. The first thing we'll look at though is pressure. And in this, I'm going 2 observations are going to be made. If I increase the pressure by pushing on the syringe, you can get an initial observation of what's happened. That is because there's less space. So if I crammed you all into a smaller space, you'd all end up getting closer together anyway. That's what's going to happen to those particles. But then if I hold it there, Le Chatelier's principle comes into effect. And the reaction, either the forward or the reverse reaction, so either this reaction or this reaction, will be favoured to create a new equilibrium system for a higher pressure. And then we need to go and explain it. Then I'm going to reduce the pressure, pull on the syringe. And because it's clamped at the end, that is going to mean that it's not going to change the number of particles in there, just the pressure. And that's also going to have an effect immediately as the particles spread out. But then the second observation, the one you put in the exam answer, is what then happens to the concentration of these 2 gases. The nice thing is one is brown and one is colourless. So if it gets darker, which reaction is favoured, forward or reverse? Have a look. Reverse. If it gets darker after I've changed something, the reverse reaction is made. If it gets lighter, it means the concentration of NO2 is going down, which is favouring the forward reaction. Well done. Okay, so the first thing I'm going to do is the easy one. I'm going to increase the pressure. I'm just going to stick my finger up there too, just to make sure. Now initially it will get darker as the particles get close together. You might find this easier to look at on the data projector. Right, so initially the particles got close together. I did have a little bit of gas escape here. So initially got a little bit darker, but then we are hopefully noticing, if we saw it on the screen, that it faded a little bit. Okay, I'll release it back to where it was. So initially the particles got closer together, which made it darker. But then, as I held it there, it started to fade in colour. That means which reaction is being favoured? Forwards. Now, if I look at the equation, and I look at the number of moles, I can actually use the Chatelier's principle to explain this. If I increase the pressure, there is less space for those gas particles. So the Chatelier's principle says the reaction that will make the fewer number of gas particles will be favoured. So the forward reaction makes 1, whereas the reverse reaction makes 2. So the forward reaction is favoured because it makes fewer gas particles. If there's fewer gas particles in total, then that will then reduce the pressure because there's fewer particles to accommodate the smaller volume of space. Any questions on that? That's one of the hardest concepts to understand. If I increase the pressure, the reaction which produces fewer gas particles is favoured because fewer gas particles per unit volume reduces the pressure. So I'm going to reduce the pressure another way. I'm going to increase the volume without increasing the number of particles. And it will get lighter. Then when I hold it there, and the screen might be easier to look at, it starts to get a little bit darker, not much. This one's not as dramatic. Okay, put it back. Okay, it's back to its original control. If I pull it out, it'll get lighter because it's got less particles per unit volume. But if I hold it, it should get a little bit darker. Okay, so again, if I'm reducing the pressure, it wants to lift the pressure. The best way to increase pressure is to make more particles. So therefore, it will favour the reaction which produces more particles, or gas particles. So the reverse reactions, that's why I've got darker again. It creates a new equilibrium position. It changes the concentration of these two things with respect to each other. You're going to learn about a thing called Kc, equilibrium constant, which we use to say are there more products or more reactants. When I change a condition, does it favour the forward or reverse reactions? So we're going to equilibrium constant later. Right, I have got some iced water now. We look at temperature. One of these reactions is exothermic and one is endothermic. And the giveaway is if I put it in cold water, iced water, which reaction will be favoured? The exothermic or the endothermic? Which one will try to heat it up? Exo. So if it gets darker, it means the reverse reaction is exothermic. If it gets lighter, it means the forward reaction is exothermic. I'm going to try and keep the pressure the same, otherwise we have too many variables. Ice there at the moment. Helps, it's trying to suck it in as well, it's trying to pull this syringe in. So it is getting lighter, and if I leave it there long enough, it's going to be dramatically lighter. It goes nearly colourless. Okay, I just can't get quite deep enough into it, too much ice. But it did get noticeably lighter, didn't it? Okay, let's make it really obvious. Is there boiled water there? Can you put that in that other beaker, please? I'm trying not to let the syringe move, because that's another variable. Just enough to dunk this in. Awesome, if you just put that there for me, please. Okay, I'll move that awesome. That out, and in without letting it push against me. Should see pretty quickly go darker. Yeah, it's pretty obvious, wasn't it? Yeah, I can't stop it pushing, it's really pushing the syringe. Okay, so it's favouring the reverse reaction, which is making it push the syringe out too, because it needs more space. Okay, so therefore, which reaction is exothermic? Forward or reverse? Good. The forward reaction, because if I made it colder, it tried to heat up and it got lighter. So it made a higher concentration of N2O4. So that means the forward reaction is exothermic. So next to this reaction over here, you write delta H is less than 0. Because we always say that the forward reaction is the one that the enthalpy changes for. That's our convention. And actually, just for your information, we normally write these in such a way that the forward reaction is exothermic. In exams, they won't do that because it's too easy. Alright, so just be aware of that. Any questions before I stop this? Right, if you go to page 206, you'll see where to write that up. It's set up and it's safe to use, so you can revisit those if you need to. Just do